this, what we first want to see is let's read the question. So we have f be a function such that f of -1 equals 1 at each point x comma y in the graph. The slope is given by this derivative. Which of the following statements is true? Now, this is the first derivative, and to do this problem and see what we have at this point, -1 comma 1, because x is -1 and y is 1, to see what it is that we want to do here, we're going to use the second derivative test. Now, what the second derivative test is and why does it make sense? So let's first get an idea of what the second derivative test says. So it just basically says that if the derivative at that point equals 0 and f double prime is positive, then f has a local minimum at c. And if the derivative is 0 and the second derivative is negative, then f has a local maximum at c. So why is this true? So this follows from a basic idea. So here's the idea, okay? If the second derivative at some point c is positive, right? That's saying the second derivative is positive, then f is concave up. And we need to have an idea of what is meant when we say concave up. This is concave up. So the idea is that it just looks like this. Concave up looks like that. Okay? So it makes sense that if you see that you have it where f prime of c is 0, so this is c right here, right? This is the x-axis, let's say, and then right here is c. F prime of c, this is f. F prime of c, the derivative is 0. And then if I take the second derivative, I could see that f double prime of c is greater than 0. It being positive implies that f is concave up, and then it is true that then this value here is a minimum. Now let's contrast this with the other idea. If f double prime of c is negative, then f is concave down. And that looks like that. And with this, you can kind of see also again that you see you have this, and then here's c, let's say. And it's very clear that f of c, the derivative, f prime of c equals 0. The slope of the tangent line is 0. And then also you could see that, you see now I have it that f double prime of c is negative, and that this point right here is a local maximum. It's at the top of the hill, right? And then this one is a local minimum because it's at the bottom of the hill. So we apply this logic to this problem here, because what you have in this case is that if you look and I plug in -1 comma 1 into this derivative, I'll get 0. But now I need to know a little bit more. I need to know whether it's relative minimum, relative maximum, maybe it's neither, or maybe the second derivative is 0, in which case you can't say. And then there's insufficient information, maybe it's C or D, you don't know. So let's see what we can get. So what I'm going to do is I'm going to find the second derivative. I'm going to do d squared y dx squared is equal to, now I got to take the derivative of the derivative. So it's going to be -2x minus, and I'm going to differentiate x times y on the side. So the derivative of x times y, I got to do product rule. The derivative of x is just x. The derivative of x is 1 times y. All right? Plus the derivative of y is dy dx. And then times x. And it's minus that whole thing. So I'm going to write it minus y minus x dy dx. And then I have plus the derivative of y squared is 2y times dy dx. And then the derivative of negative 1 is just 0. Now, this is the second derivative in terms of dy dx. Now, let's see. So I already have it. So using the second derivative test, right? If I plug in, right, this point, if I find out that the derivative is 0, right, let's see what I get. So x is negative 1. Negative 1 squared is positive 1 minus 1 minus negative 1 times 1 is negative 1, so it becomes plus 1 plus y squared. Y is 1, so it's just 1 minus 1. This here all equals 0. So I'm satisfying the initial condition here that the derivative is 0. Now I want to figure out whether it falls into case A or case B, because that will tell me whether at this point whether it's a local minimum or a local maximum. So the second derivative, right, if I plug in negative 1 comma 1 into the second derivative, let's see what I get. So negative 1, right, x, negative 1 comma 1 minus 1, y is 1, minus negative 1. And then now I know dy dx, when I plug in to dy dx, I get 0. So I could actually just eliminate this term and this term. So I get 0 there. So these terms go to 0, so I'm not even going to bother with them. 0 and 0. And the only thing I have is this minus 2x minus y, which is 2 minus 1, which is 1. So I get that the second derivative is positive. And if the second derivative is positive, then f has a local minimum at that value. And it's A as my answer. Okay, that's because the curve is going to be concave up because the second derivative was positive, right? So that means that at this point, C, it's going to be a local minimum, which was negative 1. This was along negative 1, and then this was 1 along here, along Y. Okay, something like that. I mean, the y-axis would be over here, but whatever.